So today we'll pick up where we left off last time. So we introduced distributions and test functions last time and got started on a few of the operations we can perform on distributions. So we'll continue to examine the kinds of things we can do with distributions, namely take derivatives, multiply them with functions or compose them with functions, and then we will talk about at the end of the lecture some of the applications of distributions. So we ended yesterday's lecture with a formula or a prescription for taking the derivative of a distribution. So if we want to take n derivatives of a distribution and act with that on a test function, that's the same thing as minus 1 to the n times the distribution acting on the derivative of the test function, the nth derivative. So this was our definition of the weak or distributional derivative. And so the first thing I want to discuss or show you is just first that this works for a familiar case, and then we'll look at perhaps a less familiar case and see how we can apply this formula. So one example where I bet you can guess what the result should be, but let's just use our new formalism to make sure that everything works as we expect, is that if we want to take the derivative of the Heaviside step function, which is just defined to be 1 for x greater than or equal to 0, or 0 for x less than 0. So this is a function. It induces a distribution because this is a locally integrable function. The integral of this function over any finite interval is finite. So it's a distribution as well. And you can probably guess what the derivative of this should be. But let's just check using our the new formalism involving test functions to make sure that this definition works the way we expect it to. So if we want to compute the derivative of the Heaviside distribution acting on a test function using this formula for the distributional derivative, we just get minus the Heaviside distribution acting on the derivative of the test function, which, since this is a distribution induced by this function, is just the integral of theta of x and phi prime of x. Which you can simplify. This is just 1 for x greater than 0, so you get phi prime of x dx. Or this is an integral we can do. It just gives us minus phi of infinity minus phi of 0. Now phi of infinity, by assumption, is 0, because we assume that our test functions have compact support, so they vanish outside of a finite integral. So this this term is 0, and we have two minus signs, so this just gives us phi of 0 or delta of phi, which is probably what you would have guessed. So that the derivative of this distribution is just Dirac delta. Yeah. because this works for any test function phi. So it's two distributions are equivalent. Okay.
Didn't those distributions have to be continuous?
Our distributions have to be continuous, yes.
Okay.
But continuous is maps over phi,
Okay.
not over x. Yeah. It's once again, the topological thing.
That's right, yes. Yeah. Continuous as functionals. Yes. Okay. Let's look at a somewhat more involved example. So let's suppose we want to compute the derivative of the natural log of the absolute value of x as a distribution. So the derivative of the natural log of x as a function is just 1 over x. But 1 over x is not locally integrable because the integral from 0 to a of dx diverges. So it seems like we have a problem here because, well, the answer we might expect does not induce a distribution. So 1 over x is not a locally integrable function, so it doesn't induce a function, induce a distribution. Nevertheless, we can define the distributional derivative of the natural log of the absolute value of x. And the way to do that is to first modify our definition of the distribution natural log of x acting on a test function. So we can take as a definition to be the limit as epsilon goes to 0 of the integral from minus infinity to minus epsilon plus the integral from epsilon to infinity. So basically over the real line, just with a small region of width 2 epsilon around the origin, excised. Acting, all right, and our integrand is phi of x, natural log of x. So we've just cut out a small region around 0. And in fact, we can show that in this limit that epsilon goes to 0, the cutout part vanishes. And I'll basically do that, show that in a minute. So we can take this as a definition of the distribution natural log of x, and in that case, we can define the weak derivative using our formula over here. So with that definition, the derivative is minus the limit as epsilon goes to 0 of this integral, the small region cut out, phi prime natural log of x. And if we want to simplify this expression, there's basically only one thing we can do, which is integrate by parts. We don't know what the function, the test function phi is. So if we integrate by parts, what we get is the limit as epsilon goes to 0. We get this integral, the small region can still cut out. The derivative goes on to the natural log. We get a 1 over x. And we also get boundary terms. Okay, and these boundary terms will vanish in the limit epsilon goes to 0. To see that, note that there's a common factor of the natural log of the epsilon in both terms, and this other term is basically like twice the derivative of phi at 0 times epsilon. And we've got the natural log of epsilon. And this goes to 0 as epsilon goes to 0. Epsilon goes to 0 faster than natural log blows up. So these terms, these boundary terms, disappear in that limit. That's essentially the same reason this cutout part vanishes. So, and then our expression here is this first term, this integral, is what's known as the principal value distribution. Acting on our test function phi. And so this principal value distribution, which is almost 1 over x does not induce a distribution because it's not finite for every test function, but this principal value is a modification of the function 1 over x, where we just cut out a small region around 0. And this is a distribution acting on, it gives us a finite result. We act on any test function. And this is one of the it's probably the second most important distribution that's not a function after the Dirac delta. And as we'll see in tutorial this afternoon, there's a close relationship between this principal value distribution and the I epsilon procedure that we'll use very frequently in quantum field theory. Yes, Rick?
Is this limit going to exist for any compact support to C infinity function phi? Otherwise, it's going to violate the finiteness that we have imposed in our distributions, right?
This limit?
No, the first one, which is what is defining the PV of 1 over x.
This first term?
Yeah.
Yes, this... Yes, so given the assumptions we made on phi, namely that has C infinity, has infinitely many derivatives, so it's a smooth function, and that it has compact support, this will be a finite number. We'll examine at least a related point in tutorial this afternoon. Any other questions on this? Okay, the second operation that we might like to perform on a distribution is we might want to multiply it by a function. So we can try to define this in the same way as before. So by taking inspiration from those distributions that are locally integrable functions. So let's suppose we want to multiply our distribution u, which for now we'll assume is a locally integrable function, by some other function psi, and act with that on the test function phi. Well, if u is a locally integrable function, we can just write down a simple expression for this. Psi of x, u of x, phi of x, integrated from minus infinity to infinity. So this is okay if u is a function. And we can just change the order of multiplication, group together the psi and the phi, and write this as u and psi as phi, which suggests that we should define psi u of phi to be u of psi times phi. So this matches what we'd expect for the distributions that are functions. And assuming we impose conditions on psi so that psi times phi is a test function, this will make sense for any distribution. So this will be a test function if psi is continuous and has infinitely many derivatives. So phi already has compact support. So if we multiply a C infinity function by another C infinity function that has compact support, we'll get another C infinity function with compact support. Yes?
By definition, I don't see the first line why psi is within the integral. Isn't u the distribution acting on phi?
So what we want to do is we want to multiply. So for now, we're assuming u is a function. And we want to multiply that function by another function and treat the product function as a distribution that's acting on the test function phi. Okay. And so this is our definition. Write this as a definition. And note, it only makes sense. We can't multiply by an arbitrary function. It has to be a C infinity function. So I don't watch a lot of TV, but I think there's a channel that has more information about multiplying distributions by test functions, the Sci-Fi channel. Okay, so I'm going to give you an example to see if to check that you understand what we've done so far. So let's suppose we want to multiply the distribution delta prime, the derivative of the Dirac delta, by x. So I'm going to give you a couple minutes to try to simplify this using the rules we've learned for differentiation and multiplication. Feel free to discuss with your neighbors as well. So. So you're finished. Can you just give me a thumbs up so enough of you are finished? We'll move on. I only see a few thumbs, so maybe a couple more minutes.
I have a question.
Yes.
On that board, why is phi 0 equal delta phi?
So the Dirac delta distribution is defined to be the distribution that takes as an input test function and outputs the test function evaluated at 0. I think that is the definition of Dirac delta.
Delta function. The delta distribution. That's the identity. Oh, the derivative of the identity is 1. Is the function that takes x to x. So that has derivative 1. That's why there's a 1 here. But here is
Okay, so this is like delta applied to it. It's not like delta as a function, like everything. So that's
Okay. Thumbs up if you're finished. Okay. Getting closer, I'll give you 1 more minute and we'll go over this. Okay. I realize not everyone's finished, but we'll have more practice with distributions tutorial this afternoon. So if we want to try to simplify this expression, the product of a distribution, the derivative of a distribution with a function, the first thing we need to do is act with this on a test function. Now, we can first use our multiplication rule to write this as delta prime acting on the function x times phi, which is minus delta acting on the derivative of x times phi, which we can write as minus delta acting on, if the derivative of x on x, we just get delta of phi. We get another term where the derivative acts on phi. That's minus delta time, acting on x times phi prime. So just use the product rule for derivatives. And the second term, so we've got the direct delta acting on x times phi prime. Now we know that phi prime is finite, in particular at 0, and x evaluated at 0 is 0. So this term just gives us 0 times something finite. So this term vanishes, and we're just left with minus delta acting on phi. So that tells us that we can simplify x delta prime into minus delta. Are there any questions on this example?
Please repeat why the second term vanishes.
So this term is equal to the function x times phi prime evaluated at 0, which we can write as 0 times phi prime evaluated at 0. This is finite. So something finite times 0 is 0. Yes?
So writing it this way means we are doing the multiplication first and then doing the derivative. So how would you write it if you do it the other way?
If doing it the other way, I would write it as x delta prime.
Well, but the prime is only, like you're only taking the derivative of delta.
That's right. So in the same way that if I had x times the derivative of a function, I would write it like this. If I wanted to take the derivative of x times the function, I would write it like that. So I'm using the same notation here.
Well, so when I saw the question and I thought it's, x multiply the derivative of the delta, and that would give a different
That would give a different answer. That's right.
Okay.
I'll try to be more clear in the future.
Right, okay.
Any other questions on this example? Okay, so the third operation we can perform on distributions is we can compose it with a function. So what we want to compute is u composed with f acting on a test function. As this should be familiar to you by now, we'll start by assuming that u is a function. And in that case, we can write this expression as u of f of x multiplied by phi of x, integrated from minus infinity to infinity. So this works if u is a function. And again, there's only one possible thing we can do without knowing anything about functions other than that phi is a test function, and that's to make a change of variables. So we can call y equals f of x, and to slightly simplify notation, I'll assume that I'll write f inverse as g. So if you make that change of variables, then what we get is the integral of u of y, phi of g of y times g prime of y dy. And g is just f inverse. And so this is what we would write as so this is u composed of f acting on phi. And we can write this as u acting on phi composed with g multiplied by the absolute value of the derivative of g. And so we can take this as our definition. And g is f inverse. And this makes sense for an arbitrary distribution as long as this phi of g times g prime is a test function. So we need this to be a test function. And this is guaranteed if f has infinitely many derivatives and y equals f of x has a unique solution. Or we can invert this for all y.
But it seems that aren't there gonna be, because the derivative of g is 1 over the derivative of f. Wonder
Yes.
becomes if I have the derivative, if the derivative of f becomes 0. Oh,
Yes, then this
always have to be.
this will fail then. Yes. So this works in general as long as we have this condition on f. It's sometimes possible to weaken this condition depending on the distribution u, and because the most important distribution is the Dirac delta. And for the Dirac delta, we can weaken this condition. We can define the Dirac delta composed with a function acting on a test function in a slightly more general case where we don't have to impose quite as strong of conditions on the function we're composing our distribution with. And for the Dirac delta, if we want to compose that with a function, it can be defined basically to be the same formula. I'll write it in a slightly different way. Where here f of xi is 0. So xi are the roots of f. And delta xi is a shifted Dirac delta distribution, so that delta x sub xi acting on phi gives us phi of xi. And this this works if f has only simple roots. So this is a slightly weaker condition. We don't need, we can allow f inverse to not be unique, but it does fail if there are multiple roots. And this formula is exceptionally important and will come up over and over again throughout the year. If you remember one thing from the first 2 lectures, remember this formula. It is important and will come up many times. Sorry?
What is a simple zero?
A simple zero. So for example, if we choose f of x equals x squared minus 1, this says, so a quadratic polynomial has 2 zeros. They're both have multiplicity 1. If we factorized it, it would be x plus 1 times x minus 1. By comparison, so a quadratic polynomial has a double zero at x equals 0. So we'd expect a quadratic polynomial to have 2 zeros there.
So it means the algebraic multiplicity of the zeros.
Exactly. So we can't compose the Dirac delta with this function x squared. It fails. Basically, you can think about it because this factor would be 0 in the case we had a multiple root. For this one, we wanted to compute delta of f. I can phi, that would be delta minus 1 over 2, because the derivative is 2 minus 2 at 1 plus delta 1 over 2. Acting on phi. This one, delta of f, undefined. Other questions about composition? Yes.
Assuming that our future variables, it doesn't change the limits of the function, right? The assumption of right?
This about the limits of integration? Yes. So this makes sense as long as y equals f of x has a unique solution. So basically, we're assuming that the function f is a map from the real line to the real line, and it, yeah. Okay, so we've seen what we can do mechanically with distributions, what kind of operations we can perform in them. So the next thing to talk about is what are some of the important applications of distributions. And one of the most important ones is functional derivatives. So particular in the path integral or functional integral formulation of quantum field theory, which we'll study in depth in QFT 2. Functional derivatives and multiple functional derivatives will show up all over the place. And there's a very nice systematic way to formulate functional derivatives in terms of distributions. And for many students, I found that this formulation is the easiest way to deal with functional derivatives, in particular multiple functional derivatives. But I just wanted to mention first that the procedure I'm about to describe to you is entirely equivalent to what David taught you in the classical mechanics course. So in classical mechanics, David was describing how to compute the variation of the action. And what you found in the simplest case was that the variation of the action was just the partial derivative of the Lagrangian with respect to q minus d dt partial L partial q dot. Times variation of q. So this was assuming here that S was a function of q and q dot. So David showed that to you in his classical mechanics course. So this procedure he described, where you compute the variation, is entirely equivalent to computing the functional derivative. And the functional derivative is basically this quantity in square brackets. So this is the functional derivative, and as this expression suggests, we can think about the functional derivative as a distribution. So this part here is a distribution, and it's acting on a test function delta q, which we can write as epsilon, some small parameter, times a test function. So there's a direct mapping between what you did in classical mechanics and what I'm about to explain to you. There's in particular a systematic way of computing functional derivatives. And one thing that's useful to keep in mind when we're thinking about functional derivatives is there's an analogy between functional derivatives and partial derivatives. So we can, if we have a functional, we need to compute a functional derivative, but you can think of that as a limit of, we can think about a functional as a limit of a function with infinitely many arguments. So in particular, if we were computing the variation in some quantity s that depended on a discrete set of variables, qi, what we would, to find the variation in this function of the qi, we would take the partial derivative of s with respect to qi and multiply by the variation in each of those variables. And this expression for the functional derivative is nothing but a continuum limit, or limit where the number of variables goes to infinity, in which case the sum becomes an integral, the partial derivatives become functional derivatives, and the qi's become, instead of being indexed by a discrete label, become indexed by a continuous label. So this is a useful analogy to keep in mind. It suggests many correct results and ways to manipulate functional derivatives. And the nice thing about thinking about functional derivatives in the language of distributions is that the definition of the functional derivative basically becomes the one you're all used to. From your first calculus course. So we have the functional derivative acting on a test function. That's just equal to the limit as epsilon goes to 0 of f acting on f at f plus epsilon phi minus f of f divided by epsilon. So it's exactly what you'd expect based on the first definition of a derivative you saw. And so if we want to write the left-hand side in a more, or another way we can write this, so this is the distribution, that's the functional derivative acting on the test function, so we can write this in another way. I'll put in the argument here. So basically, if you want to compute functional derivatives, you just use this expression, which is the same as, very closely analogous to the one you saw in your first calculus course. The big difference is what you get if you compute this thing is not just the functional derivative, but it's a functional derivative acting on the test function. So if we compute this side, in general, we're going to have to manipulate it in order to put it into this form so that we can read off what the functional derivative is. And to see how that works, let's go through an example. And we'll go through a number of other examples in tutorial this afternoon. So if we choose as our functional f of f equals f squared evaluated at some point x naught, then the functional derivative acting on a test function is just given by this formula up here. We evaluate f of f plus epsilon phi. We get f squared of x naught plus 2 epsilon f of x naught phi of x naught plus phi of x naught squared minus this term, which is just f squared of x naught divided by epsilon. And the first and last terms cancel. And sorry, there should have been epsilon squared here. And this term goes to 0 in the limit epsilon goes to 0. So we're just left with this one term, which is 2 f of x naught phi of x naught. So that's the result, but we need to put it into this form in order to be able to read off the functional derivative. And we can do that by putting in a Dirac delta. So we can write this as the integral of 2 f of x naught times delta of x minus x naught phi of x dx. And so this part is the functional derivative. We just compare this expression, so we get delta f. X is 2f x naught times delta x naught, or delta of x minus x naught, so depending on which notation you prefer. And so it's a very, very systematic procedure that works even in the case where f is a distribution. So we can take multiple functional derivatives using the same procedure. And we'll see some examples of that in tutorial. Does this example and procedure make sense? Are there any comments or questions? Yes.
Why is only delta x0 and not delta x minus x0?
Oh, so this is the same thing.
Okay.
Yeah.
Just notation.
Just notation.
Okay.
So in the previous board, I introduced the notation that this is delta x0. Okay, so based on the analogy with partial derivatives, you might expect that the functional derivative has a number of properties. So functional derivative is linear, has a product rule, and a chain rule. Exactly like you'd expect based on the analogy with partial derivatives. So I wrote them out explicitly in the notes. Do you want me to write them on the board here? Yes. Yeah, at least one person says. I'll write them. So linear means that if we take a linear combination of two functionals multiplied by some complex numbers, these are both functionals of f, then we just get lambda times functional derivative of f with respect to f plus the other constant times the functional derivative of g with respect to x. So that's exactly what we'd expect based on the analogy with partial derivatives. The product rule is that if we take the functional derivative of a product of functionals, f times g, with respect to f, we get functional derivative of f times g plus f times the functional derivative of g. So that's the product rule, and there are two different chain rules and two chain rules. So chain rules are, if we get the functional derivative of a functional of g of f with respect to f, can write this as functional derivative of f with respect to g of f of x times the ordinary derivative of g of f with respect to f and the second chain rule is if we have a function of a functional we can compute that as the derivative of g with respect to f of f times the functional derivative of f with respect to f.
In the product rule, for example, in the first term, the g is evaluated at f, so it is a number,
Yes, so these are value
and g is also at f.
at f. Yes.
So the x dependence is always on the derivative. For example, g of f doesn't depend on x, right?
That's right. Yes. And so notice that I've written the g on the right in the first term and in both terms. And if the functionals commute, it doesn't matter, but we'll come across functionals where things don't commute. And in that case, it's important to get the relative order of the factors correct.
But these are, at this, I mean, they're numbers now, right?
They're numbers now, but we will come across functionals later in the year where they're not necessarily real numbers.
How does multiplication between functionals work?
So far we've assumed that our functionals are maps from functions to the real numbers. So we're assuming that f of f is a real number and g of f is a real number. So we have the product of two functionals that we just use the multiplication for real numbers. We'll consider more general functionals later in the year. But for now, everything is a real number. Okay. And we'll have some practice in tutorial using these properties. So you can always compute any functional derivative just directly from the definition, but as in ordinary calculus, using these rules will save you a lot of time.
Is there some standard space where all of this happens? Like we haven't paid too much attention to analysis of it, but it's like there's some standard space where the functions are usually taken, something where it surely works, so that if in the case that, because you said that we will later encounter functionals that won't be numbers, and that would probably be because there must be some hypothesis which we're not stating, so that in that case when we get to when things fail, we can know, oh yeah, it
Right.
failed because this hypothesis wasn't.
So this works as long as this side exists. So we need to be able to make sense of this limit. And for now, we're assuming that these functionals are all real valued. So this limit makes sense if we're just assuming real valued functionals. Okay. So the next application I'd like to discuss is how to think about Green's functions as distributions. So David has also been telling you about Green's functions. And I'd just like to present a slightly different perspective. So as you know, a very common problem we like to solve is solving this equation for y, where L is a linear differential operator. And y and f are functions. And solving this equation is, well, the natural way we would try to solve this equation is just by finding the inverse of L. So if we can find some object L inverse, then the solution to this equation is just y is L inverse times f. And this L inverse here is what's known as a Green's function. So this is just a very, I'm leaving out some details, but this is just a very schematic way of thinking about what we're doing when we're finding a Green's function. And it's useful to think about, well, there's another context in which we might want to solve equations in this way, which is if L was some matrix and y and f were vectors, basically we would try the same procedure. And there is a useful analogy between solving this type of differential equation and solving a matrix equation. And I'd just like to point out. So think about the matrix version as being finite dimensional. Some finite dimensional matrices, and the differential equation version as being infinite dimensional. So the analogy is that if we have vector v, that's like a function f. We have a component vi that's like the value of the function at a point f of x. We have a matrix M like an operator O, or in this case I called it L. If we have a matrix element Mij, that's, and this part of the analogy may not be as familiar to you. It's called the integral kernel of the operator, called K of x and y. And what is meant by integral kernel of an operator? So if we wanted to multiply a matrix times a vector and take the ith component of the result, what we would do in terms of components is multiply Mij times Vj, summing over j. The analogous statement in terms of operators and integral kernels and functions would be that O acting on f evaluated at the point x is equal to, the sum becomes an integral. We have the integral kernel of the operator O, and we have the function evaluated at y. So this equation is the analog, the infinite dimensional analog of this matrix equation. And this object here is known as the integral kernel of this operator O. And much of what we're going to do in QFT2 is going to be formulated in terms of integral kernels of operators. And this analogy goes surprisingly far. So in most cases, you can just think about the finite dimensional version and use this analogy to figure out what the correct equation is in terms of operators and functions. The reason I call it an analogy, though, is that there are sometimes subtleties involving boundary conditions. So assuming everything works out with boundary conditions, then this is generally the way you'll proceed when we're dealing with operators and integral kernels. And the last element of the table is that if we have the identity matrix, the analogous quantity is the Dirac delta. Okay, so let's just spend a minute to think about how to interpret the Green's function problem in terms of this analogy. So we're finding a Green's function. Basically, we're trying to find the inverse of a differential operator. So in terms of matrices, what we mean by the inverse of a matrix is the inverse of a matrix should, when we multiply by the matrix, we should get the identity matrix. So the analogous quantity, analogous statement is that L times L inverse should be equal to the Dirac delta. And L inverse is what we call the Green's, or it's the operator corresponding to the Green's function. And this equation suggests why I've included this topic in the distributions section of the course. Well, this is an equation that explicitly involves a distribution. So in general, the Green's functions are going to be distributions, not necessarily functions. And well, if we want to find the Green's function, so the Green's function is the integral kernel of this operator. And so we need to write down the component form of this equation. So m times n inverse ij is equal to Kronecker delta ij. And the component form of this equation would be so here g is the Green's function, and c, and so the component form of this equation then becomes y of x is the integral of the integral kernel of this operator, which is the Green's function. times function on the other side, f of c dc. And if we can check rather easily that this solves our original equation. We take L acting on y of x. We get the integral of Lx g of x c f of c, where Lx just means the derivative is with respect to x. So this, by assumption, is delta. So we get delta x minus c f of c dc, which is f of x. So this works if the Green's function solves that. So this is probably a familiar application, but in tutorial tomorrow we'll see some more involved examples where this analogy will be very useful in constructing the correct expression that involves the integral kernels of the operators. So we'll see an example that will be directly applicable to the QFT in tutorial tomorrow. That to me the easiest way to think about is using this analogy. Any comments or questions on this? Okay, so one other application is of this technique is solving an equation like this perturbatively. So it might not always be possible to solve an equation like this exactly, but if there is some part of the differential operator that we can invert, and there's a small perturbation, we can use perturbation theory to solve this equation. So if we assume that our solution has some 0th order term, some term that's order lambda, and some higher order terms that we don't care about at the moment, then we can solve this equation perturbatively. So at 0th order, we want to solve L naught y naught equals f. The solution, which we'll assume we can find, is y naught is L naught inverse f. If we want to go to next order, L naught y equals f becomes L naught y naught. Then we can have a first order term in L and 0th order term in y, or a 0th order term in L and a first order term in y. All the other terms will be order lambda squared or higher. This should be equal to f. You know this term is f. And so this term cancels with this. And we get a solution that is y1 there should have been a lambda here. first order term is lambda times L1. Get minus lambda. We bring this term to the other side times L naught. Y1 is L naught inverse. L1 Y naught is L naught inverse F. And so we see that we get a perturbative solution that involves just products of our solution to the free problem, the problem without any perturbation, multiplied by our perturbation. And this is basically the technique we're going to use in quantum field theory to construct perturbative solutions. We'll frame it in a slightly different language, but it's essentially the reason why all our solutions in quantum field theory are going to be products of free Green's functions with some operator that characterizes the perturbation. And we can repeat this procedure to higher order. In the simplest context, this is essentially what we're doing in quantum field theory when we're solving problems perturbatively. So this, first of all, are there any questions on that? Yes.
We have a y naught and then a y1, and you said that's of order lambda. Why is that of order lambda?
So by assumption, I'm assuming that y1 is order lambda, so that yn is of order lambda to the n.
Okay.
That's just how I'm distinguishing y0 from y1. Okay, so to conclude our section on distributions, so we've seen the various operations we can perform on distributions: derivation, multiplication, composition. We've talked about two important applications, two Green's functions and functional derivatives. And there's one important thing we can't do that I haven't discussed so far, but it's something that will come up, but it's not a well-defined operation. So the theory of distributions is linear, which means that the product of two distributions is not generally well defined. So it doesn't make sense to, for example, square the Dirac delta. We can consider Dirac deltas in higher dimensions. That's perfectly fine. But if we're dealing with a one-dimensional problem and we run across a delta squared, that's an ill-defined quantity that we can't make sense of based on what we've learned so far. Nevertheless, that's something we are going to encounter in quantum field theory. We're going to have to come up with other resolutions that we haven't not yet discussed. But that's an important caveat to keep in mind about what we've discussed. So it's not known how to extend this theory of distributions to include a well-defined product. Okay, so where we're going next time, we will move on to a completely different subject. We'll discuss asymptotics, asymptotic series, methods for constructing them, and we'll also briefly discuss the gamma function, which is both a nice simple example to illustrate many of the ideas and techniques we'll be discussing, as well as an important application to physics that we'll see in tutorial. So that's where we're going. Are there any comments or questions? If not, I'll see you this afternoon.